The laser is already on when you walk in. Midnight in the lab has a particular silence, fans whispering, the faint ozone bite of electronics, and that thin, unwavering line of red light cutting through the dark like a verdict. It hits a slab on the optical table, and the beam does something it should not do. It bends the wrong way. Not a reflection. Not a scatter. A clean, impossible turn, like reality briefly forgot its own rules. So here's the question we're here to audit together. Can you actually build an invisibility cloak, or is invisible just a word we use when we don't look closely enough? Come closer. Put your hands on the edge of the table with me. Feel the vibration of the building, the hum of the power supplies. If you wanted light to pass by you as if you weren't here, no outline, no shadow, no glint in anyone's camera, what would it take? Not in a fantasy sense. In the cold, operational sense that physics respects. Because invisible isn't a vibe. It's a measurement. It's a claim about detectors. When you say, I can't see it, you're usually talking about your eyes, those two wet lenses with retinas tuned to a thin slice of the electromagnetic spectrum. But the universe watches with more than eyes. Cameras. LiDAR systems firing near-infrared pulses and timing their return. Thermal cameras reading mid-infrared radiation like a heat confession. Radar sweeping entire landscapes with microwaves. Even a cheap phone sensor sees differently than you do. So for this investigation, we'll start with visible light, because it's intimate. It's the light you've lived inside of your entire life. And then we'll widen outward, because invisibility that only works for one kind of looking isn't invisibility. It's stage lighting. Here's the audit standard, simple enough to remember, brutal enough to matter. If light scatters off you into someone's detector, you exist to that detector. Scattering is evidence. It's the universe's paper trail. Right now, as you're watching this, you're visible because photons are bouncing off your skin, your clothing, your eyes, carrying information about you outward. Every moment you've ever been seen is literally an event in which your body edited a passing wave of light and sent the edited copy into someone else's world. So let me ask it in a way that hits the human nerve. If every moment of your life is witnessed by reflected light, could you ever truly step outside the universe's gaze without leaving a trace? To answer that, we have to get precise about what the light is doing. Light doesn't travel like a tiny bullet train of particles unless you force it into that story. Most of the time, the more useful picture is a wave, a moving sheet of influence. Imagine an infinite field of tall grass in the wind. A gust moves through, and you can see the ripple, crest, trough, crest, rolling across the field. That ripple has a shape. That shape matters. That moving shape is what we'll call a wavefront, the leading edge of same phase. Light, like the line of a marching band where every foot hits the ground at the same time. If the band's line tilts, the direction of the music changes. Now, when light encounters an object, your face, a rock, a fog droplet, what makes it visible is not simply that light hits it. It's that the object forces the wavefront to change. It can reflect, refract, absorb and re-emit, or scatter in complex patterns. In every case, the outgoing light carries information about the object. And that brings us to the lever we'll be pulling all night, refractive index. Refractive index is one of those terms that sounds like a textbook until you give it a pulse. Here's the metaphor. Imagine light as a crowd trying to move across a city. In open streets, people move fast. In a dense market, they slow, bump, and weave. The refractive index is a number that tells you how dense the city feels to the wave, how much the material slows the phase of the wave and twists its marching line. Phase velocity is the speed of the wave's rhythm, how fast the crests move. It's not always the speed of energy, and that distinction is going to matter later when the story turns strange. But for now, let's take the familiar route, because the familiar route is where the shock hides. Picture a glass of water. A straw sits inside. You've seen the illusion, the straw looks broken at the surface. That's refraction, light changing direction because it changes speed when it crosses from air into water. There's a law for this, and it's almost poetic, Snell's law. People write it like a formula, but I want you to feel it as a principle. Light chooses the fastest legal path. Like a hiker trying to get from the beach to a point inland, maybe you sprint on the sand, then slow in the forest. The shortest distance isn't always the fastest time, so the hiker cuts an angle, spending less time in the slow region. Light does the same. The angle it chooses depends on the refractive index, how slow the medium makes that wave rhythm. Here's the first question that should start to itch. If bending light is just reshaping wavefronts, could you reshape them so perfectly that light goes around an object and returns as if it passed through empty space? No shadow. No glint. No evidence. You can already feel where this is heading. And it's not magic. It's engineering, so extreme it starts to look like sorcery. But before we cloak anything, we have to break a belief that most people don't realize they're carrying. That refractive index is always positive. That materials always slow light down, in the same kind of way. If you were designing the universe from scratch, you'd probably assume that too. Nature mostly behaves that way in everyday materials. But physics doesn't promise it. Physics only demands consistency. So we pivot, quietly, like a door in the back of the lab that you never noticed. It's 1968, not literally, but in spirit. The air is different. The optimism of prediction hangs in the room. A physicist named Victor Veselago runs a thought experiment so clean it feels like a dare. What if a material had both negative permittivity and negative permeability? Let's decode those without draining the wonder. Permittivity, epsilon, is how much a material allows electric fields to form inside it. It's like how easily the crowd in the city can be pushed and rearranged when an electric rhythm passes through. Permeability, mu, is the magnetic counterpart, how the material responds to magnetic fields, how easily it lets magnetic influence thread through. In ordinary materials, epsilon is often positive in the visible range, and mu is basically close to 1. Magnetic response at optical frequencies is hard because electrons can jiggle fast enough to respond electrically, but getting them to loop like tiny magnets at visible light speeds is another level. Veselago's insight was startling. If both epsilon and mu were negative in some band of frequencies, the refractive index, the square root of their product, could be negative. Not imaginary, not undefined negative. And if the index is negative, Snell's law doesn't break. It obeys, but it flips. Instead of refracting to the opposite side of the normal, the transmitted beam bends to the same side as the incoming beam, like it's cheating. Like it took a path that should be illegal, except it isn't. The math says it's allowed. The physics says, if you can build the material, I'll honor the result. Now come back to the lab with me. Under the bench light, the slab in your hand doesn't look like a new element. It looks like a patterned circuit board. Etched lines. Little rings with gaps, split ring resonators. Wire arrays. Repeating motifs, like a microscopic city planned by an obsessive architect. This is the first seduction of metamaterials. They're not made of new atoms. They're made of geometry. A metamaterial is a material whose behavior comes not from its chemistry, but from its structure, especially when that structure is smaller than the wavelength you're using. Subwavelength. That word matters. Because if the unit cell, the repeating block of the pattern, is much smaller than the wavelength, the wave can't see the individual pieces. Like a stadium wave, from far away you don't see each person standing, you see a smooth moving ring. The light averages over the microstructure. It experiences an effective medium. That's the effective medium approximation, the idea that complicated structures can act like a simple material with tuned epsilon and mu. But if the unit cell isn't small enough, if the pattern is comparable to the wavelength, the wave starts to notice the seams. It scatters. It diffracts. And scattering is the enemy. Scattering is evidence. Now here's the image to hold in your mind, because this is where negative refraction stops being a symbol and becomes a sensation. In normal materials, energy and wavefront travel together. The wave crests march in the same general direction that the energy flows. If you could paint arrows on the light, the phase velocity, and the energy flow, called the pointing vector, roughly point the same way. In negative index media, something uncanny happens. The phase travels opposite the direction of energy flow. It's like watching a conveyor belt move boxes to the right while the belt's painted stripes slide to the left. The cargo goes one way, the pattern goes the other. That reversal is not a parlor trick. It's the core of why people started whispering about cloaks. Because if you can control phase, if you can sculpt the wavefront like clay, you can attempt something audacious. You can try to make the wavefront leave a region untouched. And the first time you truly see that, not in a formula but in your bones, something changes. You realize, bending light isn't magic, it's controlled reshaping of wave fronts, and wave fronts can be engineered. Now, let's take the next step, the one that launches 1,000 headlines. We're going to draw a cloak. Not a cape. Not a fantasy fabric. A map. On the whiteboard beside the optical table, I sketch a circle, an object we want to hide. Then I sketch lines, light rays heading toward it. Normally, they hit the object, scatter, cast a shadow, and tell the world, something is here. But what if we could do something more radical than blocking or absorbing the light? What if we could remove a region of space from the story? Imagine space as a coordinate grid on a sheet of rubber. If you push the rubber aside and stretch it smoothly around the hole, lines that once went straight now curve around. Yet from far away, the grid can look undisturbed, as if the hole simply isn't part of the map. That's the intuition behind transformation optics. It's the idea that Maxwell's equations, the rules light obeys, can be written in a form that lets you treat certain material designs as if they were curved space. You don't literally warp spacetime the way gravity does. You do something more accessible and, in some ways, more surgical. You warp the electromagnetic experience of space. You design epsilon and mood to guide the field lines the way a carefully carved riverbed guides water. In the seductive version, in the version that shows up in simulations, rays approach the cloak, curve smoothly around the hidden region, and reunite on the other side. No scattering. No reflection. No shadow. The background looks untouched, like the object never existed. And in that moment, you feel the pull. You can almost hear the future. But then the lab air changes again, because this is the science audit. And we don't fall in love with a picture. We stress test the claim. So we start asking the questions that reality always asks. First, what color of light? Because real materials, and especially metamaterials, are dispersive. That means their refractive index changes with frequency. The cloak that works at one wavelength is usually a cloak that fails at another. If you tune the structure so green light flows perfectly, what happens to red? To blue? To the near-infrared beam from a security camera? To the broadband sunlight that contains everything at once? A perfect cloak for white light would have to guide a whole orchestra of frequencies, each with its own speed and phase behavior, around the object without tearing the harmony. And nature is not generous with that kind of coordination. Second, loss. Metamaterials, especially those attempting negative index at optical frequencies, often absorb. The structures rely on resonances, little electromagnetic, ringing, behaviors in the split-ring resonators and their kin. Resonances are powerful, and they're fragile. They come with dissipation. Absorption means the cloak eats part of the wave. That shows up as dimming, or heating, or a spectral fingerprint, anomalous dips in transmission that a spectrometer can read like a lie detector. You can hide a reflection and still reveal yourself as a shadow of missing photons. Third, angle and polarization. Polarization is the orientation of the wave's electric field, like whether the light is wiggling up, down, or left-right as it moves. Many metamaterials respond differently depending on polarization, because their geometry has preferred directions. So a cloak might work if the incoming light has one polarization, and fail if it's rotated 90 degrees. It might work beautifully when the light comes from the front, and betray you when it comes from the side. And the world rarely offers you one direction, one polarization, one carefully prepared beam. The world is messy. And invisibility, to be real, has to survive mess. Now we reach the deeper tax, the one you can't pay with better fabrication alone. Time. If you detour light around an object, you increase the path length. Even if the beam emerges in the same direction, it may arrive late. That delay can show up as a phase shift for a continuous wave, or as a time delay for a pulse. And if you send a broadband pulse, a femtosecond flash, a packet of many frequencies, the cloak must not only redirect it, but preserve the entire waveform. Think about what that really means. A pulse is a story told in time. It has a beginning, a peak, a tail. If the cloak stretches it, smears it, or delays parts of it differently, dispersion again, then even if your eyes see nothing, an instrument sees the distortion. Causality, the principle that effects follow causes, leaves fingerprints in dispersive systems. There are deep relationships, like the Kramer's, chronic relations, that tie together how a material bends light and how it absorbs it. You don't get to tune one without touching the other. So the question becomes sharp enough to cut: can you guide light around a region without introducing any detectable phase delay, time delay, or distortion across a broad band of frequencies? If you can't, then a perfect cloak isn't just hard, it may be forbidden in the absolute sense people imagine. And then there's the manufacturing reality, the part the simulation never sweats. To cloak visible light, you need structures on the scale of hundreds of nanometers. That's smaller than many bacteria. It's a world where smooth doesn't exist the way your hands understand it. Tiny roughness becomes mountains to a wave. Finite unit cell size becomes a diffraction grating. Small misalignments become scattering centers. And scattering is evidence. This is where the dream meets the workbench. Even if the design is right, the build has to be perfect enough that the wave never catches on a seam. Now pause with me, because the mind naturally tries to escape into either cynicism or hype. I want neither. I want clarity. So let's run 3 thought experiments that feel almost like moral tests for a cloak. First, the perfect cloak paradox. If nothing scatters, can you see out? Because to see, light from the outside must enter your eye. That means light must penetrate the cloaked region, interact with your retina, and be absorbed. Absorption is interaction. Interaction is, in principle, detectable. You might argue that the cloak could guide light into your eyes and then reconstitute it perfectly, hiding the exchange. But then we're asking for something even more extreme, not just hiding an object, but hiding an entire set of measurements happening inside. Invisibility starts to look less like not being there, and more like managing information with impossible discretion. Second, the rain test. Imagine you walk outside while cloaked. Rain hits you. Water splashes. Droplets split and scatter. Even if you are invisible to visible light, are you invisible to the turbulence you create in air? To the sound of footsteps? To the heat you emit in infrared? To the pressure waves you generate when you move? Invisibility to one sensor is not invisibility to reality. Stealth is always a spectrum. Hide from which channel? Which detector? Which distance? Which conditions? Third, the pulse test. A friend across the room fires a femtosecond pulse and measures the returning field with interferometry, sensitive not just to intensity, but to phase and time. Does your cloak preserve not only direction, but the full waveform? Does it return the pulse as if it crossed empty space? Because if it doesn't, if there's even a tiny delay, then you are still there. Not as a shadow, but as a timing anomaly. And timing anomalies are the currency of modern detection. LiDAR is literally a stopwatch with a laser. This is the core mystery, now fully exposed. Invisibility isn't a single trick. It's an attempt to control every degree of freedom of a wave, direction, phase, polarization, spectrum, without paying the universal taxes of loss and causality. So where does that leave us? It leaves us with a truth that is both humbling and empowering. Cloaking is real in limited domains, and those limits aren't a failure, they're the lesson. Because when we build even partial cloaks, we learn how to sculpt fields. We learn to build designer space. That reframes the entire story. The real achievement of these devices isn't vanishing like a ghost. It's precision so high that we can persuade a wave to behave as if geometry itself has been rewritten. And that has already worked, just not in the all-seeing, all-angle, all-color way science fiction trained us to expect. In practice, the strongest demonstrations have been at longer wavelengths, microwaves, for instance, where fabrication is easier, losses are often lower, and you can build unit cells that are comfortably sub-wavelength. Researchers have cloaked small objects under controlled conditions, specific angles, narrow frequency bands. It's not a person walking through a sunlit street. It's a carefully prepared experiment. But it's not nothing. It's a proof that the equations can be negotiated with hardware. And there are practical cousins that already shape the world. Radar stealth, for example, often relies less on exotic materials and more on shaping, controlling scattering by controlling geometry, redirecting reflections away from the detector. Then there's scattering cancellation, using coatings that produce an equal and opposite scattered field to reduce the net signature. Not disappearance. Signature management. Now, if you want to see where the frontier is moving, keep your eye on 3 directions. 1. Metasurfaces. Instead of bulky 3D metamaterials, we design thin, patterned surfaces, like electromagnetic skin, that impose abrupt phase shifts. They can steer, focus, and shape wave fronts with less material, often less loss, and more manufacturability. 2. Active cloaks. If passively sculpting fields runs into bandwidth limits, you can add adaptivity, components that sense incoming waves and respond in real time, injecting energy to cancel scattering. That's not a simple cloak, that's a system. And systems can cheat constraints that passive materials cannot, at the cost of power, complexity, and new signatures. 3. Computational cloaking. Hardware plus algorithms. You accept that the physical world won't give you perfect invisibility, so you pair sensors and processing to subtract your signature from measurements, especially in engineered environments. And beyond the visual, the concept generalizes. Acoustic cloaking, guiding sound around objects. Thermal cloaking, guiding heat flow as if an object weren't there. Each domain has its own physics, its own constraints, its own version of scattering as evidence. And that brings us to the deepest implication, one that is philosophical, but not fluffy. Visibility is an information exchange. To be seen is to leak information into a field. To be invisible is to prevent information leakage across many channels at once. In that sense, invisibility isn't the absence of you. It's the mastery of boundaries, what crosses from you to the world and what doesn't. Now come back to the lab for the final moment. The laser is still there, a thin red line. We switch it off. Darkness returns, and with it the ordinary weight of things. The slab is still in your hand, solid, real, a piece of engineered geometry that never once stopped existing. The magic was never disappearance. It was control. And nature's response to control is always the same. You can do astonishing things locally, but the universe keeps the books. Energy, information, time. The moment you try to erase your interaction with light, you still have to reconcile what happens to the photons, what happens to the phase, what happens to the heat, what happens to the delay. Nature allows illusions. It protects consistency. And it never offers them for free. So here's the synthesis, what we've actually learned tonight. An invisibility cloak, in the strict sense, means controlling scattering so perfectly that, to a detector, you leave no optical evidence. Metamaterials and negative refraction show us that wave fronts can be engineered, sometimes in ways that look impossible, because refractive index is not a sacred positive number. It's an emergent property we can design with structure. Transformation optics shows the blueprint, guide fields around a region as if space itself has been remapped. But the audit reveals the costs. Dispersion limits bandwidth, loss leaves signatures, angle and polarization dependence fracture the illusion, and causality shows up as delay and distortion, especially when you probe with pulses. Which leads to a contemplative takeaway you can carry into your own life, not as trivia, but as a lens. Imagine every interaction you have, every conversation, every footprint you leave online, every room you walk into, as a kind of scattering. A tiny redistribution of information that tells the world you were there. Now ask yourself, if you tried to move through a day leaving no trace at all, not emotional, not digital, not physical, what would it cost? What would you have to give up? Sight? Warmth? Contact? And finally, the next great question, the one that opens the next door. If invisibility is ultimately about controlling information flow in fields, then what happens when the field isn't light, but time itself? If time is an illusion, what does that say about the memories you hold most dear? If you want to keep going, click the video on the end screen, because it's the next step in this audit of reality, and it will deepen this story in a way that might change how you see your own life. And if you want more investigations like this, where we don't just accept science headlines, we interrogate mechanisms, subscribe. Not for hype. For clarity. One last thing before you go. If you had to choose, would you rather be invisible to cameras, or invisible to radar? Just answer with one word and tell me why in a sentence. I'll be reading every response.